Section formula. Now, you might be wondering, what exactly does this formula do? Essentially, it gives us a mathematical way to find the position vector of a specific point that sits on a line segment connecting two other points, based on a particular ratio. Think of it as a way to pinpoint an exact location along a path if you know how the path is divided. But this isn't just an abstract classroom concept. The section formula is actually a fundamental tool used in many real-world fields. Whether you are looking at physics to calculate forces, engineering to design structures, or even navigation to determine precise coordinates along a route, this formula is essential for determining exact locations. Welcome, everyone. Today, we are going to dive into a very important topic in vector algebra, the section formula. In the next few slides, we will break down how to apply this formula for both internal and external division, and I'll show you a practical example to see it all in action. Internal division. Think of internal division as a point sitting right in the middle of a path. Specifically, internal division occurs when a point, let's call it R, lies directly on the line segment PQ, positioned somewhere between points P and Q. To understand how to calculate this, let's look at the scenario. Imagine we have 2 points, P and Q. We represent their positions using position vectors, which we'll call a vector A for point P, and vector B for point Q, both measured from an origin. Now, suppose there is a point R that divides this line segment PQ internally into a specific ratio, which we write as m to n. This brings us to the most important part, the formula. To find the position vector of point R, which we denote as vector R, we use the following equation. R equals the quantity m times vector B plus n times vector A, all divided by the quantity m plus n. I know that might look a bit complex at first, so let's break it down into a simple 4-step process you can use every time. First, identify the position vectors. You need to clearly determine which vector is A, representing point P, and which is B, representing point Q. Second, identify the ratio. Look at the given ratio and pull out your values for m and n. Third, perform the cross multiplication. This is a crucial step to avoid mistakes. You take the first part of the ratio, m, and multiply it by the far vector, which is vector B. Then, you take the second part of the ratio, n, and multiply it by the near vector, which is vector A. Finally, sum and divide. Add those two resulting vectors together, and then divide that entire sum by the total number of parts in your ratio, which is m plus n. Now that we understand the general purpose of the section formula from our introduction, let's dive into our first specific case, internal division. I know that might look a bit complex at first, so let's break it down into a simple 4-step process you can use every time. Once you master this process, you'll find that calculating internal points becomes much more intuitive. In our next slide, we will look at what happens when the point falls outside the segment, which we call external division. External division. Now that we have mastered internal division, where the point sits between our two endpoints, let's look at the second possibility, external division. In this case, the point R still lies on the same infinite line passing through P and Q, but it doesn't sit between them. Instead, it falls outside the segment PQ. To visualize the scenario, let's say we have points P and Q with position vectors A and B relative to our origin. If we say point R divides the segment PQ externally in the ratio m to n, what we are really saying is that the distance from P to R compared to the distance from Q to R maintains that specific ratio of m over n. Now, if you look closely at the formula, you'll notice it looks very similar to the internal division formula we just studied, but with one crucial difference in the signs. The position vector R of point R is equal to m times vector B minus n times vector A, all divided by the quantity m minus n. To make sure you apply this correctly in your exams, follow this 4-step breakdown. First, identify your position vectors A and B. Second, identify your ratio values m and n. Third, apply the difference. just like before, you'll multiply the ratio values by the opposite vectors, but this time, instead of adding them, you subtract the product of n and vector A from the product of m and vector b. Finally, divide that entire resulting vector by the difference of the ratio terms, which is m minus n. Keep this subtraction in mind, because as we will see in the next slide, when the ratio is perfectly balanced, we get a very special case called the midpoint. The midpoint formula. Now that we have mastered the general formula for internal division, let's look at a very important special case, the midpoint formula. Think back to our previous slide, where we discussed how a point R can divide a line segment in any ratio, m to n. Well, the midpoint is simply the most balanced version of that. It is a special case of internal division where the point R sits exactly in the center, dividing the segment PQ into two perfectly equal halves. So, what does this look like mathematically? In this specific scenario, because the two segments are equal, our ratio is simply 1 to 1. This means that our values for m and n are both equal to 1. If we take our internal division formula that we just learned, where r equals m vector b plus n vector a, all over m plus n, and we substitute our new values, replacing m with 1 and n with 1, something very elegant happens. The numerator becomes 1 vector b plus 1 vector a, and the denominator becomes 1 plus 1. When we simplify that, we are left with the position vector r equals vector a plus vector b, all divided by 2. It is a much simpler formula, and it's essentially just finding the average of the two position vectors. This will be incredibly useful when we move on to our practical navigation example in the next slide. Real-world example, navigation. Imagine we are working in the field of navigation. We have two radio towers, which we will call Tower P and Tower Q. Their locations are defined by position vectors. Vector A equals 2 I hat plus 4 j hat, and vector B equals 8 I hat plus 10 j hat, with the units in kilometers. A technician's task is to place a signal booster at a specific point, point R, such that it divides the distance between these two towers internally in a ratio of 2 to 1. Let's walk through the solution step by step. In step 1, we begin by clearly listing all our known values from the problem. We have vector A as 2 I hat plus 4 j hat, vector B as 8 I hat plus 10 j hat, our ratio value m is 2, and our ratio value n is 1. In step 2, we recall the internal division formula we studied in the previous slide. We will use the formula where vector r equals the quantity m times vector b, plus n times vector a, all divided by the sum of m and n. Moving to step 3, we substitute our specific values into this formula. This gives us vector r equals 2, multiplied by the quantity 8 I hat plus 10 j hat, plus 1, multiplied by the quantity 2 I hat plus 4 j hat, all over the quantity 2 plus 1. In step 4, we perform the scalar multiplication. We distribute the 2 into the first vector and the 1 into the second. This results in vector r equals the quantity 16 I hat plus 20 j hat, plus 2 I hat plus 4 j hat, all divided by 3. In step 5, we combine the like terms through vector addition. We add the I hat components together and the j hat components together. This simplifies our expression to vector r equals the quantity 18 I hat plus 24 j hat, all divided by 3. Finally, in step 6, we simplify the final vector by dividing both terms by 3. This leaves us with vector r equals 6 I hat plus 8 j hat. To conclude, we have found that the position vector for the signal booster is exactly 6 I hat plus 8 j hat. As we will see in the next few slides, mastering this calculation is essential to avoid common errors in more complex problems. Now that we have understood the theoretical concepts of internal and external division, let's apply them to a practical, real-world scenario. Key takeaways. First, let's revisit internal division. Remember, this is the scenario where our point, R, sits directly on the line segment, nestled between points P and Q. The formula you'll need to memorize is R equals m times vector B plus n times vector A, all divided by the quantity m plus n. Next, we have external division. As we discussed earlier, this is when point R lies on the line passing through P and Q, but it's located outside the actual segment PQ. The formula here is very similar, but notice the crucial change in the sign. R equals m times vector b minus n times vector a, all divided by the quantity m minus n. Now, don't forget the midpoint formula. This is just a special, simplified version of internal division. When the point divides the segment into two perfectly equal halves, our ratio is 1:1. This simplifies our math beautifully to r equals vector a plus vector b, all divided by 2. Finally, if you find yourself struggling to remember which ratio value goes with which vector, just remember the cross rule. This is a lifesaver. In both the internal and external formulas, you always multiply the ratio value m, which is associated with point P, by the far vector, which is vector b, associated with point Q and vice versa. You multiply n with vector a, just think of it as a cross-multiplication pattern. All right, let's bring everything together. We have covered a lot of ground today, so let's review the key takeaways to ensure you have the core concepts firmly in mind before we move on to the common pitfalls. Keep these rules in your toolkit, because in the next slide, we're going to look at some common mistakes that even the best students make when applying these formulas. Common mistakes. First, watch out for incorrect vector pairing. This is perhaps the most frequent error I see. When you are calculating the formula, do not multiply m with vector and n with vector b. It is easy to pair them with their corresponding points, but remember the cross rule we discussed earlier. Since m represents the distance from point P, it must be paired with the vector of the opposite point, which is vector b. Always cross-multiply to ensure accuracy. Second, be very careful with sign errors during external division. When we moved from internal to external division in the previous slides, you notice the formula changed from addition to subtraction. Students often forget to change the sign in the denominator to m minus, and when you are working outside the line segment, that subtraction is crucial. Third, make sure you are not confusing position vectors with displacement vectors. When you are identifying your values, ensure you are using the position vectors, which we called vector A and vector B, representing the points relative to the origin. Do not accidentally use the vector PQ, which represents the displacement between the 2 points. Finally, always double-check the order of the ratio. The values of m and n depend entirely on the direction of the ratio. You must check if the ratio is given as p to q or q to p, because swapping these will change which value is assigned to m and which is assigned to n, ultimately changing your entire calculation. Now, before we wrap up today's lesson, I want to pause and discuss some common pitfalls. Even if you understand the formulas we've covered, it is very easy to make small errors that can lead to the wrong final answer. Let's look at 4 specific mistakes to watch out for. Keep these tips in mind, and you will find much more success with the section formula. Great job today!